Good day. This is Module 2. I will now provide you some problem solving involving vectors in the plane. So let's recall the formula that we have learned in our first lesson, that is vectors in the plane. So we have here vector by components as well as magnitude, length, or norm of a vector. So we have here the formula in two space, where we have here a vector v whose components are defined as v1, v2, and its magnitude or length or norm is given as this notation. It's like a double absolute value sign. So this is magnitude or length or norm of a vector v is equal to the square root of v sub 1 squared plus v sub 2 squared. If we have now a line segment whose initial point is at A, and we have the coordinates are x1, y1, and we have a terminal point at point B, whose coordinates we have it as x2, y2, then we can define a vector on line segment AB denoted as v equals AB, and whose components is equal to the difference of the coordinates of these two points A and B, and that is starting from the coordinates of point B minus the coordinates of point A. And as we can see, it is here x2 minus x1, y2 minus y1 as the components of your vector B or vector AB. And in finding the magnitude of your vector B or magnitude of your vector AB, so we have here the square root of quantity x2 minus x1 squared plus quantity y2 minus y1 squared, which is similar to distance formula between 2 points. For a vector in 3 space, we have here now the vector v, whose components we have it as v1, v2, v3. And its magnitude represented as the double absolute value sign, which is also denoted as magnitude length or norm of vector v. It is equal to the square root of v1 squared plus v sub 2 squared plus v sub 3 squared. And if you have a line segment whose initial points are given A and B with the corresponding coordinates, we have at point A x1, y1, z1, and point B at x2, y2, z2. So we can now define the vector v of your line segment AB equals, we have again the components of your vector AB or vector v defined as the difference of the coordinates of your 2 points starting with point B minus your point A. So we have x2 minus x1, y2 minus y1, and z2 minus z1. And in getting the magnitude, length, or norm of this vector v or line segment AB, so that is now equal to the square root of the quantity of x2 minus x1 squared plus quantity y2 minus y1 squared plus quantity z2 minus z1 squared. Then we also have the formula or the concept on unit vectors. It says here, if v is not equal to 0, then we have v over magnitude of v is a unit vector in the direction of v. Then the equation v equals magnitude of v times v over magnitude of v expresses v as its length times its direction. A vector v of length 1 is called a unit vector. The standard unit vectors are I, whose components are 1, 0, 0, j equals 0, 1, 0, and k equals 0, 0, 1. Any vector v whose components are v1, v2, v3 can be written as a linear combination of the standard unit vectors as follows. So we have your vector v equals v1, v2, v3, which is equal to v1, 0, 0 plus 0, v2, 0 plus 0, 0, v3, where we can factor out the components v1, v2, v3 on these three vectors. So we have v1, and it is now 1, 0, 0 plus v2, and it is now 0, 1, 0 plus v3, it is now 0, 0, 1. As you can see, these components that we have here in our vectors are your vectors I, j, k. So we can now write this vector v as a linear combination of the standard unit vectors as v sub 1i plus v sub 2j plus v sub 3k. Then another formula that we will be dealing with is the vector determined by length and angle. It says here, if vector v is non-zero vector with its initial point at the origin of an xy coordinate system, and if angle theta is the angle from the positive x-axis to the radial line through vector v, then the x components of can be written as magnitude of v cosine theta and the y components as magnitude of v sine theta, and hence can be expressed in trigonometric form as v equals magnitude of v cosine theta sine theta, also equal now to magnitude of v cosine theta I plus magnitude of v sine theta j in ijk or ij format. Let us work now on these examples. So we have here, find the component form of the vector. That is in exercise 9 to 16. But we only have here 9, 12, and 13. So let us solve first for number 9. We're going to find the component form of the vector PQ, where P equals 1, 3, and Q equals 2, negative 1. So for this problem, the components of your vector PQ will be equal to, you have the coordinates of your point Q minus the coordinates of your point P. So we have that formula a while ago, okay? And that will be in bracket notation, that's 2 minus 1. Then you have negative 1 minus 3. So therefore, the components now of your vector PQ is equal to 1, negative 4. So that's the answer for problem number 9. For number 12, we have find the component form of the vector, the sum of the two vectors AB and vector CD, where we have A equals 1, negative 1, B equals 2, 0, C equals negative 1, 3, and D equals negative 2, 2. So when we denote this in mathematical symbol, it is now the sum of the two vectors AB and CD is also written as AB plus vector CD. So with that, we will have the components of your two vectors defined first. Let's define first the components of your two vector AB, which is now, again, you have the terminal coordinates minus the initial coordinates of your 2 points B and A. So we have here now 2 minus 1. Then you have 0 minus 1, that is 0 plus 1. So with that, simplifying, we have the answer 1, 1. For CD, we have it as, this is for vector CD. So we again find the components using the formula. So the coordinates of the terminal minus the coordinates of the initial point. So we have negative 2 minus 1, that's negative 2 plus 1. Then you have 2 minus 2. So therefore, the answer now is negative 2 plus 1 is negative 1. 2 minus 3 is also negative 1. So with that, when we now define the two vectors, getting its sum, so we have here the components 1, 1 for AB plus for vector CD, it is negative 1, negative 1. So adding now the components, 1 plus negative 1 will be 0. 1 plus negative 1 for the second component is also 0. So this is also known as zero vector because a zero vector is a vector that has 0 components. So this is now your answer for number 12. So we can also write it as zero vector.